All right. We find ourselves talking about acceleration again. Acceleration continued. And we are going to talk about the big three. All right, these three particular equations are incredibly useful in solving problems involving constant acceleration. Once again, we are going to say this involves constant acceleration. Okay, this is important. If we have a changing acceleration, these equations no longer apply. The reason that we even bring them up then is because of how many times we see systems in which there is a constant acceleration, mostly involving the Earth and gravity. Now, what we're going to do is we're going to take the original equation that we had for acceleration, which is change in v over t, all right, and we're going to rewrite it. We're going to take time, move it over to the other side. We're going to have delta v. I'm going to rearrange the whole equation. Looks like this. A t. Okay, so the t, we multiply both sides by t. Okay, if you like to see all the steps. T's cancel on that side. At delta v. Okay. Now once again, we rewrite this like this. V naught plus equals at. Okay. So final speed minus initial speed equals acceleration times time. Now we're going to rewrite this one final time, and this will give us the first of the big three. Okay, A-T. There it is. This is the first of the big three. I call this just the first equation. Okay, that's number one. Now, if you think about what this means, it makes sense, but you have to think very clearly, okay? How fast something goes in the end depends upon a couple of things. It depends on how fast were you going in the beginning and how long were you accelerating. Right? And that should make sense, right? If you're going at a constant speed for a long period of time and you didn't accelerate at all, this term goes away. Okay? So how fast are you going in the end? Well, you're going as fast as you were in the beginning. Initial speed equals final speed. That's pretty nice. Now let's say you were going at some speed, okay? And you accelerated for a certain amount of time. How fast would you be going? Well, whatever your acceleration is times your time plus however fast you're going to begin with equals your final speed. Okay, so that one makes sense. Now, I'm not going to necessarily derive the second one. Suffice to say, if you take the integral of, wow, that kind of brightened, that was weird. It kind of brightened it wrong. Anyway, if you take the integral of this particular equation, okay, you use some calculus on it. You take the integral of that equation, you will find another equation, okay, that looks like this. This is the first of the big three. There it is. The second of the big three is the equation that you get when you take the integral here. And what that looks like is this. X final equals X initial plus V initial times time plus 1/2 the acceleration times the time squared. Now, if you are in calculus, listen up for the next couple seconds. If you're not, this is fine too if you want to listen. But it's a little bit confusing unless you remember how calculus works. So what we do is we take this object, we turn it into a velocity. Velocity, as we defined it before, was just a change in position over time, right? So we have an expression for velocity. This is position over time. Now, if we take the integral over time, what will end up happening is this term turns into a special term right here. This term will pick up a time term, and this term right here will pick up a half and a time term as well. Okay? Now, once again, for those taking calculus right now, you'll learn this later. For those of you not taking calculus, and you will eventually, I don't know, you'll learn it later too, I guess. If you don't take calculus, that's fine. Why are we even talking about this? Anyway, this is the second of the big three. All right. Now, the third of the big three happens when you shove equations together. Now, if we want to just write it out, that is fine by me. However, it's always fun to try to shove equations into other equations, right? So if you're interested in what the derivation is, we can just shove these two equations together. And that's what we'll do right now, okay? First thing I'm going to do, I'm going to separate the x's back over to the same side. There we are. Equals v naught times t plus 1/2 a t squared, okay? This equation over here has a t in it. Let's solve for t over there. Okay, that'll look like this. Vf minus Vo over acceleration equals time. Don't believe me? Try it yourself, okay? Now, t, shove this in right there. Okay, we find ourselves with xf minus xo equals v naught times time. Well, crap, time is an illusion. The only time now is party time. And are we clear? Vf minus v initial over a. Yes, I did that right so far. Minus 1/2 times acceleration times that whole thing squared. Whew. Am I right? Okay. So now distribute. Do the square there. I need more space. Gosh dang it, I always do this to myself. And then he talks softly to himself for a while. What's that all about? Mr. Beaver, what are you doing? Right? Why is he talking so softly? Okay, there's that. Minus 1/2 times a times this whole thing squared. So we've got over a squared on the bottom. That's not a squared. What am I doing? Honestly, life. Am I right? Okay, and then on top, if you square that, that's a polynomial. It'll end up being vf squared minus 2 vf v initial plus v initial squared. All right? Now you may be saying to yourself, you ran out of space. Well, guess what? Not for long, baby. Okay, here we are. Equals. Okay, now we're going to take what we did a moment ago, and we are going to rewrite it. Okay, so let's double check what we had. We had vf v naught minus v naught squared over a plus 1/2. Now, what we can do with these a's, do you see how there's one on top and there's a squared on the bottom? We can cancel one of those. 1/2 times vf squared minus 2 vf v naught plus v naught squared over a. Now, if you guys are mathematicians, if you're mathemagicians, you will see that we can do some stuff here. There's an a on the bottom of both of these fractions. So what we can do is multiply both sides by a. Cancels that on this side. We find an a on top up here. Another thing we can do is we can multiply by 2. I know that'll send a 2 over here, but that's okay. Ah, crap. Don't do that. Don't do that to me. And you'll see why here in a moment that's important. Okay? Actually, let's do that in the next step. Step by step, right? Step by step. Okay, there's that. Equals vf v naught minus v naught squared plus 1/2 times this mess, vf squared minus 2 vf v naught plus v naught squared. Huh. Okay, so I'm going to multiply both sides by 2. Okay, well, let's multiply everything by 2, right? So there's a 2 that's going to go out here, 2 goes out here, 2 goes out here. Cancel, cancel. This one sticks around and multiplies into both of these. We're left with 2a xf minus xo equals 2vf v naught minus 2 v naught squared plus vf squared minus 2 vf v naught plus v naught squared. Right? Right. Now, do you see it? Do you see the wonderment? Do you see this term? Do you see that term? That one's negative. That one's positive. Bye. See ya. Do you see this term? See that term? Yeah, do you? Those two will add together to equal a negative v naught squared, 1 v naught squared. So we're left with 2a xf minus xo equals vf squared minus v naught squared. And this is the third of the big 3. You might be saying that was a very long derivation. You are correct. However, there is a reason for all this. Okay, there is a reason, I promise. Okay, I'm going to rearrange it just ever so slightly. Vf squared equals v naught squared plus 2a xf minus xo. Okay, that's number 3. Okay, now, what was the whole point of all that? Why did we do that? That is what I ask myself a lot. Anyway, why did we do that? Well, I'll tell you. We have a lot of variables that we're going to be messing with. We're going to be messing with position. We're going to be messing with initial position. We're messing with initial speed. We're going to be messing with final speed. And we're going to be messing with acceleration. We're messing with time. The first equation. What is it missing? This first equation is missing xf and xo, right? So position. The second equation, right? This guy right here, 1/2 at squared. What is this one missing? Looks like this one's missing vf. Third equation, this one right here, I'll rewrite it, whatever, doesn't matter, equals v naught squared plus 2a, change in x position. What is this one missing? This one's missing time. No xf, no vf, no time. If you want to find something out about something in your system, if you want to find out a quantity, and you are missing too much stuff, you can use these equations, okay? Let's say you were trying to find your final speed, you had this, if you're trying to find your final speed, you had this, but you did not have either of your x positions, you would use this first equation. If you did not know how fast your thing was going in the end of your problem, you could use the second equation. If you don't know how long stuff was happening for, you could use this third equation, okay? So that's the reason that we did all this, okay? It might seem a little bit long and drawn out, especially this last part, but it is important because we can use these to predict basically everything about a system that's accelerating.